Welcome back to the deep dive. I hope you are ready to settle in because today we are doing something a little bit different.
Yeah, it's a bit of a departure for us, isn't it?
It is. We are taking a step away from the abstract world of, pure software and stepping into a world that is usually defined by sensory experience, by tradition, and frankly by a fair amount of romance.
Well, usually we're dissecting code or maybe looking at economic trends. This feels a lot more
Yeah,
artisanal.
exactly. But today we're opening a bottle of something very special. But we aren't just drinking it, we are deconstructing it. We're taking a look at the ancient, somewhat mysterious world of wine tasting and asking a very modern, very provocative question.
Which is,
Can a computer taste better than a human?
it's a fascinating clash of cultures,
Yeah.
really.
Yep.
On one hand, you have the homologist, the sommelier, the centuries of tradition where the golden nose is king. It's seen as this art form, deeply subjective, almost poetic.
Mm.
And then on the other hand, you have the cold, hard logic of data mining. You've got algorithms, chemical vectors, regression analysis, art versus science.
And the source material we are covering today is really the battleground for this clash. We are looking at a paper titled Modeling Wine Preferences by Data Mining from Physicochemical Properties.
Right.
This was published in the journal Decision Support Systems way back in 2009. The authors are Paulo Cortez, Antonio Cerdera, Fernando Almeida, Telmo Matos, and Jose Reis.
And it's worth noting the collaboration here right off the bat. This wasn't just, a bunch of computer scientists sitting in a basement crunching random numbers they found on the internet.
No, not at all.
This was a partnership between the University of Minho, specifically their Department of Information Systems, and the Viticulture Commission of the Vinho Verde region in Portugal, the CVRVV.
So you have the heavy hitters of data science working directly with the people who actually certify the wine. That lends a lot of weight to the data we're going to look at today.
Absolutely.
Mm-hmm.
It means the domain expertise baked right into the data set from the very beginning. This is real-world stuff.
Okay, so here's the mission for this deep dive. We are effectively turning this paper into an audio lecture. We want to understand the how. How do you teach a machine to predict whether a wine is, say, a 3 out of 10 or an 8 out of 10 based purely on chemistry?
Yeah, and we're going to explore the specific techniques they used. We'll get into things like support vector machines, neural networks, and we're going to see how they used a really, really massive data set of Portuguese Vinho Verde wine to basically create a digital wine critic.
All right, let's unpack this. Before we get into the algorithms, the ones and zeros, we need to set the scene, the lab bench, if you will. We need to talk about the wine itself. Vinho Verde, I've had it. It's delicious, usually a bit fizzy. But what exactly are we dealing with here?
So Vinho Verde is a unique product. It comes from the Minho region, which is up in the northwest of Portugal. And it's a very, very economically significant export for the country.
How significant are we talking?
Well, between 1997 and 2007, the paper says exports increased by 36%. It accounts for a huge chunk of all Portuguese wine production. So that's a big deal.
And for anyone who hasn't had it, just to be clear, it's not green wine like the color green, right?
Right.
The name can be a bit misleading.
Right. No, Verde here refers to young.
Yeah.
It's meant to be consumed fresh, soon after it's bottled.
Mm.
Characteristically, it's medium in alcohol, it's got high acidity, and also that slight effervescence you mentioned, that little spritz, very popular in the summer.
Okay.
But because it's a denomination of origin product, a DOC, the quality control is incredibly strict.
And that leads us to the problem, right? The bottleneck. Why do we even need computers to do this? I mean, don't we have plenty of people who would love to be paid to drink wine all day? It sounds like a dream job.
You would think so.
Yeah.
But the certification process is mandatory.
Yeah.
Every single batch has to be tested. And this is partly for health reasons, to make sure there's no adulteration or anything dangerous. Yep. But it's also for quality assurance. If you buy a bottle that says Vinho Verde, it needs to taste like Vinho Verde. And at the time of this study, this whole process relied heavily on human tasting panels.
Human tasting panels? That sounds complicated.
It is. It means real people sitting in a room blind tasting samples. The problem is that's slow. It's expensive.
Yeah.
And humans. Well, humans are human. We have bad days. Our palates get fatigued after a few samples. It's incredibly subjective.
Yeah, I can imagine.
The authors of this paper highlight that taste is the least understood of the human senses. So if you're relying solely on that for a massive industrial certification process, it becomes a major bottleneck.
So the goal isn't to fire the humans. We're not building a robot sommelier to replace everyone.
No, and that is a really key distinction they make. The goal is to build a decision support system. Think of it as a tool. If you can use a computer to screen the wines rapidly based on lab tests, which are cheap and fast to run, you can do a couple of things. You can flag the ones that need more human attention, or you can assist the estheologist. So if the computer says this is an 8 and the human taster says this is a 3, that huge discrepancy tells you something is up. Maybe retaste it. Maybe check the
It's
sample.
like a second opinion, a very fast, very objective second opinion.
That's it, exactly.
Okay, so to train this computer, they needed data. And looking at this paper, they didn't just use a handful of bottles. This is not a small-scale experiment.
No. And this is one of the things that makes this study stand out. In the data mining world, specifically when you talk about wine, there's a very famous data set called the UCI wine data set.
Oh, yeah, I think I've seen that one.
It's been used in thousands of computer science classes. It's a classic. But it only has 178 examples. It's tiny.
A toy data set, basically. So what did this study use?
This study uses real-world certification data collected over a period of almost 3 years, from May 2004 to February 2007. They have 1,599 samples of red Vinho Verde.
Okay, that's already a lot.
And a whopping 4,898 samples of white Vinho Verde.
Wow. So nearly 6,500 wines total. That's a different league.
This whole different ballgame.
Yeah.
This allows for much more robust statistical modeling. You're not just finding quirks in a small sample, you're finding real patterns.
And for each of these thousands of wines, they have the target, the thing they're trying to predict.
Exactly. The target is the sensory score given by the human experts. And this is important. At least 3 professional blind tasters graded each wine. The scale was 0, which is very bad, to 10, which is excellent.
And they took the average score?
The median, actually.
Yeah.
Which is smart because it's less sensitive to a single outlier taster having a really off day.
Good point. And looking at the distribution of grades in the paper, it seems like most wines are just okay. They're not all showstoppers.
That's just the reality of production, isn't it? The data follows a pretty standard normal distribution. Most wines are a 5 or a 6. They're average, perfectly acceptable table wines.
Right.
You get very few wines that are truly terrible, down at a 3. You get very few that are excellent, up at an 8 or a 9. And that actually makes the prediction task harder.
Why is that?
Because the computer has fewer examples of the extreme wines to learn from. It has thousands of examples of what a 6 looks like, but maybe only a couple dozen of what a 9 looks like.
Right. It's easy to spot a unicorn if you see them all day, but if you only ever see horses, you might not recognize the unicorn when it shows up.
That's a great analogy.
Okay, so we have our target, the median human score. Now let's talk about the inputs, the variables. What are we actually feeding the computer? It's not tasting notes, right?
No, absolutely not. We are feeding it chemistry. Cold, hard numbers. The paper lists 11 physicochemical input variables. These are standard tests that would be run in a wine lab during certification anyway.
Let's run through these because I think it's really important for you, the listener, to understand that we aren't feeding the computer things like hints of blackberry or a note of leather.
No, it's purely objective data. So let's break them down. First, you have fixed acidity. This is mostly tartaric acid. It's one of the main acids found in grapes. It gives the wine its basic structure, its backbone.
Okay. Fixed acidity. Then there's volatile acidity. Is that different?
Very different, and critically so. Volatile acidity refers largely to acetic acid. And if that's too high,
That's vinegar.
that is vinegar. It's usually a sign of spoilage from bacteria. So high fixed acidity can be good. It adds tartness. But high volatile acidity is almost always a major fault.
Got it. Vinegar bad. Next.
Number 3 is citric acid. This is found in small quantities, but it can contribute to the freshness factor, which, as we said, is crucial for a young wine like Vinho Verde.
Right.
Then we have residual sugar. This is pretty self-explanatory. It's the sugar left over after fermentation stops. It's what determines if the wine is dry or sweet. And in the white wines in this data set, the sugar ranges all the way up to 65.8 grams per liter.
That sounds like a lot.
It is, though the average is much lower, around 6 grams. But it shows the diversity in the samples.
Okay, so that's sweetness. What else is in the mix?
Next is chlorides, which is essentially the salt content sodium chloride, mostly.
Salt in wine.
In small amounts. It can come from the soil or the water. After that, we have 2 different measurements regarding sulfur. This is important. You have free sulfur dioxide and total sulfur dioxide.
Sulfur, that sounds unappealing. I always see contains sulfites on the label.
It's absolutely essential, though. SO2 is a preservative. It's an antioxidant and an antimicrobial. It stops the wine from turning into that volatile, vinegary mess we just talked about.
Okay, so what's the difference between free and total?
Think of it like this. Free SO2 is what's currently active and available to protect the wine. It's the soldier on guard duty. Total SO2 is the entire reservoir, the soldier on guard plus all the soldiers back in the barracks. You need enough total to keep replenishing the free part, but if you have too much, you get that burnt match smell, and it can mask the fruit aromas.
Okay, a delicate balance. What else?
Next up is density, just mass per unit volume. This is closely related to the alcohol and sugar content. Sweet dessert wine is much denser than a dry, light white wine.
Makes sense.
Then pH. This is another measure of acidity, but it's on that logarithmic pH scale. It tells you the strength of the acid. Most of the wines in this study are between a pH of 2.7 and 4.0, so quite acidic.
And the final two?
The final two are really interesting. First, sulfates. Now, this is distinct from the sulfur dioxide we just mentioned. This refers to potassium sulfate levels. And as we will see later on, this variable ends up being surprisingly important.
Oh, interesting. A bit of foreshadowing.
And finally, number 11 is alcohol. Just the percentage of ethanol by volume. In this data set, it ranges from about 8% on the low end to a pretty punchy 14.9% on the high end.
So that's our cocktail. 11 numbers that define the liquid in the bottle. No romance, no poetry, just a vector of chemical measurements.
That's the input.
So now we move to section 3. The methodology. This is the technical lecture part of our deep dive. We have the data, we have 11 inputs and 1 output. How do we turn it into a prediction?
Well, the first thing to understand is the type of problem this is. The authors are very clear. They are framing this as a regression task.
As opposed to a classification task. Can you break that down?
Yes, sure. A classification task would be putting the wine into discrete buckets. Let's say good, average, and bad. You're just assigning a label.
Right.
But here, the grades are ordered. 0 to 10. The order matters. A 7 is better than a 6, which is better than a 5. And crucially, the distance between the grades matters. If the real grade is a 7 and our computer predicts a 6, that's a much, much better error than if the computer predicts a 3.
So regression preserves that order and that sense of distance.
Exactly. It's predicting a continuous value, which we then round to the nearest grade.
Okay, so they tested 3 main contenders, 3 different algorithms to build this regression model. Let's introduce the fighters.
In the blue corner, we have the old classic, multiple regression, or MinR SPOQR. This is the statistical standard. It's been used for decades in all sorts of fields.
What's the core idea behind it?
It basically tries to find a linear relationship. It assumes you can draw a straight line or a flat plane in higher dimensions through the data. It tries to create a simple formula like quality, 2 alcohol, plus 1.5 acidity, 5 volatile acidity, and so on.
Okay, so what are the pros and cons of that approach?
The big pro is that it's very easy to interpret. You get that equation, you can look at it and say, okay, for every 1 point increase in alcohol, the quality score goes up by 2. It's transparent.
But the con?
The con is that wine chemistry is almost certainly not linear. The relationships are complex. A little bit of acidity might be good, but too much is terrible. There are interactions. The effect of sugar might depend on the level of acidity. MinR really struggles to capture those complex curves and interactions.
It's too simplistic for something as complex as wine.
Probably, yes.
Okay, so that's the old guard. Who is in the red corner? The next challenger.
The next challenger is neural networks, or NN. Specifically, they use a type called the multi-layer perceptron. This is a bio-inspired approach. It's designed to loosely mimic the structure of neurons in the human brain.
How so? Can you walk us through that structure?
Sure. So you have an input layer. For us, that's our 11 chemical variables. Each one is a neuron. These input neurons are all connected to a hidden layer of neurons in the middle.
Okay.
And each one of those connections has a weight, a strength. The neurons in the hidden layer sum up the signals they get, and then they fire based on an activation function, in this case, a logistic function, which creates a nice S-shaped curve. Then that hidden layer connects to a single output node, which spits out the final quality score.
And how does it learn? How does it figure out the right weights for all those connections?
It uses a process called backpropagation. It's really just trial and error on a massive scale. It makes a guess, it looks at the real answer, it sees how wrong it is. That's the error. And then it goes backward through the network, adjusting all those tiny weights just a little bit to reduce the error for the next guess. It does this thousands and thousands of times.
It sounds incredibly powerful. It can learn those nonlinear shapes that multiple regression couldn't.
It can. It's a universal approximator, meaning it can theoretically learn any function. But there's a catch,
Right.
or a couple of catches.
I was waiting for that. What are they?
One big one is overfitting. A powerful neural network can essentially just memorize the training data. It'll be perfectly accurate on the wines it's already seen, But then you show it in a new bottle of wine, and it completely fails because it didn't learn the general pattern. It just learned the specific noise.
It memorized the answers instead of learning the method.
That's a perfect way to put it. The other problem is what's called local minima. Imagine you're trying to find the lowest point in a huge mountain range. That lowest point is the lowest possible error for your model. A neural network might walk down into a nice little valley and think, this is it, this is the bottom. But there's actually a much deeper canyon, the true global minimum, over the next ridge. It gets stuck in good enough solution instead of the best one.
Okay, so it's powerful, but it can be brittle and get stuck. And finally, the third contender, the challenger.
And this is the one that was really gaining traction in the data mining community at the time this paper was written: support vector machines, or SVMs.
Okay, I've heard of these, but they always seemed a bit like a black box. What makes them different?
The core concept is fascinating, and it's all about changing your perspective. Imagine you have all your data points plotted on a piece of paper. You've got good wines and bad wines, and they're all mixed up. You can't draw a simple straight line to separate them. What an SVM does is it uses a mathematical trick called a kernel function. They used a Gaussian kernel in this study to map those points into a much higher dimensional feature space.
Okay, you're losing me a little. Can you give us an analogy?
Absolutely. Think of it like this. You have a bunch of red and blue balls all mixed together on a flat pool table. You can't separate them by just laying down a cue stick.
No, they're all jumbled up.
But what if you could magically levitate all the red balls 1 foot into the air? You've just added a third dimension height. Now, it's super easy to just slide a flat sheet of cardboard between the red balls floating in the air and the blue balls still on the table.
Ah, I see. The sheet of cardboard is the separator?
That sheet of cardboard is the separating hyperplane. The kernel function is the magic that levitates the balls. The SVM's job is to find the absolute best place to put that sheet of cardboard, or, in our case, for regression, to find the best tube that captures the trend of the data.
And there is a specific concept mentioned in the paper that seems really central to this. It's called the epsilon insensitive loss function. That sounds like a sci-fi weapon.
It's a brilliant mathematical trick, and it's what makes SVM so robust. In normal regression, like our multiple regression model, you try to minimize every single error. Every tiny deviation of every data point from your line counts against you. You're a perfectionist.
Okay.
In SVM regression, you draw that tube or that cylinder around your regression line. The width of that tube is epsilon.
So it's like a margin of error.
Exactly. And here's the trick. Any data point that falls inside that tube is considered correct enough. The algorithm completely ignores its error. It is insensitive to it. It only cares about, it only penalizes the points that fall outside the tube.
So why is that better? It seems like you're just ignoring errors.
Because it makes the model robust to noise. It stops the model from getting obsessed with the small stuff, from chasing after tiny, irrelevant fluctuations in the data. It forces it to focus only on the significant deviations, the real outliers.
It learns what to ignore.
Precisely. And that, combined with the fact that SVMs are mathematically guaranteed to find the global minimum, the absolute best fit for the parameters, not just a local valley, makes them incredibly powerful and reliable.
Okay, so to recap, we have our three contenders: the linear ruler, which is multiple regression, the artificial brain, the neural network, and the high-dimensional geometry tube, the SVM. But you can't just plug the data in and press go, right? You have to tune these things. These models have knobs.
Exactly. And this brings us to section 4 of the paper, optimization. Every model has what are called hyperparameters. These are the knobs you have to turn to get best performance.
What are the knobs for these models?
For the neural network, the big one is the number of hidden nodes. How many neurons do you put in that middle layer? Too few, and the model is too simple. It's stupid. Too many. And it has too much power. And it just memorizes the data. It overfits.
Then for the SVM?
For the SVM, with a Gaussian kernel, the main knobs are C, which is the cost of this classification, and gamma, which controls the shape of that kernel function. How much do you levitate the data points, to use our analogy?
And usually finding the right settings for these knobs is a nightmare of just trial and error, brute force.
It can be. It's called a grid search.
Yeah.
And it can take forever. But the authors here did something very clever. They combined this model selection process with variable selection.
And variable selection means trying to figure out which of those 11 chemicals actually matter, right?
Yes. Do we really need to know the density? Is the chloride level just noise? Because if you feed a model garbage data or irrelevant data, it performs worse. It confuses the signal. So you want to strip it down to only the essential predictive variables.
And to do that, they used a technique called sensitivity analysis. How does that work? It sounds complex.
It's actually quite intuitive when you break it down. You start by training your model, let's say the SVM, on all the data. Then you perform a little experiment. You take one variable, let's say alcohol. You hold all the other 10 variables, acidity, sugar, etc., steady at their average value. Then you wiggle the alcohol value across its entire possible range. You slide it from low alcohol to high alcohol, and you just watch what happens to the model's predicted quality score.
And if the predicted score changes a lot as you wiggle the alcohol?
Then alcohol is a highly sensitive, highly important variable. The model is paying close attention to it. High variance in the output means high importance of that input.
And if you wiggle, say, the chloride level back and forth, and the predicted score stays exactly the same, flat as a pancake,
then chlorides are irrelevant to this model. The model has learned that it doesn't care about the salt content. You can probably delete that variable without hurting performance.
So they use this sensitivity idea in what they call a backward selection procedure.
Right. It's a step-by-step process. You start with all 11 variables. You train the model. Then you run the sensitivity analysis on all 11 inputs. You find the one with the lowest sensitivity, the least relevant one.
And you kick it out.
You kick it out. Then you train a new model with just 10 variables. And you repeat the process. Check sensitivity, find the new loser, kick it out. You keep doing this, going from 11 to 10 to 9, until the model's performance on a validation set starts to get worse.
At which point you know you've gone too far and just cut out a useful variable.
Exactly. And that's how you find the optimal subset of variables for that particular model.
So what was the result of that? Did they end up with just like 3 or 4 super variables?
This was one of the really interesting findings. Surprisingly, no. On average, across all their models, they only deleted about 0.9 to 1.8 variables.
So they kept almost everything.
Most of the time, the best models kept 9, 10, or even all 11 of the inputs. This is a really important validation of the industry standard. It turns out that the 11 lab tests the certification boards have been running for years are actually all useful. They all contribute some unique piece of the puzzle to predicting quality.
That's reassuring for the chemists, I bet. They aren't wasting their time running useless tests.
Not at all. The data proves their work is valuable.
Okay, let's get to the main event, the part everyone's been waiting for. Section 5, the showdown. We've set up the experiment. We've tuned the models. Which one actually predicted the wine quality the best?
To determine the winner, they looked at a few different metrics. The main one they report is AAD, which stands for mean absolute deviation.
What's that in simple terms?
It's just the average distance between the prediction and the real grade. So if the real grade was a 6 and the model predicted a 6.7, the absolute deviation is 0.7. You just average that over all the thousands of wines. Lower is better.
Okay, simple enough. But they also use these things called RAC curves.
Right, regression error characteristic curves. It's a way to visualize the performance, but the paper explains it using a much more intuitive concept, which is tolerance.
Yes, and I think the tolerance idea is crucial for you, the listener, to really understand the accuracy claims they're about to make. Can you break down tolerance?
I can. So let's say we set the tolerance, which they call T, to 0.5. This means we count a prediction as correct if it's within 0.5 of the real grade. Now, since the human grades are all integers, 5, 6, 7, this effectively means the computer's prediction has to round to the exact correct grade.
That's a very high bar, very strict.
It is. It's the hardest test. Then you can relax the tolerance. Let's say we set T 1.0. This allows the prediction to be off by 1 full grade in either direction. So if the human gave the wine a 6, any prediction from 5.0 to 7.0 would count as a hit. It's an acceptable range for a support system.
Okay, so with all that said, who won?
The support vector machine, SVM, was the clear, unambiguous winner. It outperformed multiple regression and the neural networks in pretty much every single metric, and it was especially dominant on the large white wine data set.
Okay, give us the numbers. How good are we talking?
Okay, so for white wine, if you look at a very strict tolerance of T 0.25, meaning extremely precise, the SVM was almost twice as accurate as the other methods. But let's look at the more practical numbers that you can really wrap your head around.
Let's do it.
For predicting the exact grade, that's T 0.5, the SVM got it right about 64.6% of the time for white wine and 62.4% for red wine.
Okay, so around 64%. That might not sound amazing to some people, you know. You barely passed the test, a C-.
You really have to consider the context, though. Random chance, given the number of grades, would be way, way lower. And remember, human tasters disagree with each other, too. If you put two human experts in a room, they're not going to agree 100% of the time. So getting a machine to match the media human score exactly two-thirds of the time is actually incredibly impressive.
That's a great point. It's not about being perfect, it's about being as good as or better than the existing process.
Exactly, but the number gets really, really impressive when we widen that tolerance just a little bit.
To T1.0, being off by 1 grade is acceptable.
Yes. When we look at that T1.0 tolerance, the accuracy shoots way up. For red wine, the SVM was 89.0% accurate.
89%.
And for white wine, it was 86.8% accurate.
So you're saying that nearly 9 times out of 10, the computer is either spot on or it's just 1 grade off. It's almost never wildly wrong. It's not going to call a great wine terrible or a terrible wine great.
Correct. And for a quality control application, for a decision support system, that is incredibly viable. If the computer says 6 and the human says 7, that's fine. It's in the same ballpark. The system works.
So why did the SVM just crush the neural network? I feel like in the modern era, we're always told that neural networks are the smartest things around, the ultimate solution.
Well, the authors argue it comes down to a few things we discussed. First, that global minimum versus local minimum issue. The SVM is mathematically guaranteed to find the optimal solution for the data. The neural network might have just gotten stuck in one of those good enough valleys. And second, the SVM is better at handling outliers because of that epsilon-insensitive tube. It doesn't get distracted by the weird, noisy wines as much as the neural network does. It has a kind of built-in robustness that was perfect for this kind of messy biological data.
So the SVM is our champion. But for me, the most interesting part of this paper isn't just that it worked, it's how it worked. This brings us to section 6, opening the black box. Because they used that sensitivity analysis, they could actually look inside the winning SVM model and see what makes a good wine according to the computer.
Yes. This is where the data science really turns back into enology. This is where the chemistry meets the tasting notes. They were able to rank all 11 inputs by their importance, and the results provided a genuine aha moment that I think even surprised the researchers themselves.
Okay, so what was it? What was the number one most important, most predictive chemical factor?
For both red and white wines, the number one predictive factor was sulfates.
Sulfates. Really? Not alcohol, not sugar. I feel like I only ever hear about sulfates when people are complaining about getting a headache.
Exactly. There's a lot of consumer mythology and misinformation around sulfates. But in this context, we are talking about potassium sulfate. And the expert insight provided in the paper here is absolutely fascinating. They suggest that the sulfate level isn't directly about the taste of the sulfate itself.
So it's not that we just love the taste of potassium sulfate in our wine.
No, almost certainly not. It's a proxy. It's an indicator for something else. Their hypothesis is that sulfate levels are related to the nutrient levels that were available for the yeast during the fermentation process.
Okay, go on.
Healthy, well-nourished yeast means a clean, robust, and complete fermentation. And a healthy fermentation produces the best metabolic byproducts. And those byproducts are the esters and aromatic compounds that make a wine smell and taste complex and delicious.
Whoa, so the computer, by looking at thousands of examples, figured out that high sulfates equals happy yeast and happy yeast equals tasty wine.
Precisely. It's a second-order effect that a human taster would never identify. You never sip a wine and say, ah, excellent yeast nutrition.
But the data shows, with statistical certainty, that it's the strongest single signal for quality in this entire data set.
That is genuinely cool.
Yeah.
Okay, what was number 2? What came after sulfates?
Alcohol. It was ranked very highly for both red and white. And generally, in this data set, higher alcohol content correlated with higher quality scores.
Why do you think that is? Is it just because people like a stronger buzz?
Well, partly, perhaps. But chemically speaking, alcohol adds body and mouthfeel to a wine. It contributes to the perception of weight and texture on the palate. It also acts as a solvent that carries many of the flavor and aroma compounds. A watery, low-alcohol wine often just feels thin and unsatisfying.
So there's a balance, obviously. You can't just dump vodka in and make it good.
Of course. But within the typical range for Vinho Verde, a bit more alcoholic strength was consistently preferred by the tasters.
Okay, and were there significant differences between what the model learned about red versus white wine? Oh, absolutely. Distinct differences. For white wine, after sulfates and alcohol, the next most important factors were residual sugar and citric acid.
Which makes perfect sense. White wine quality is so often about that perfect balance between sweetness and tartness. the sweet-sour balance.
Exactly. It's all about that perception of freshness. For red wine, on the other hand, the model identified volatile acidity as a major factor, but in a strongly negative way.
So it learned the vinegar is bad rule.
It learned it big time. The sensitivity analysis showed that as volatile acidity goes up, the predicted quality score just crashes. The model learned to detect that critical vinegar fault purely from the numbers.
So what's amazing is that the computer basically confirmed standard enological theory. Alcohol is generally good, vinegar is definitely bad. But it also elevated sulfates to this most valuable player status that might have been underappreciated before.
It shows that the model isn't just finding random, spurious correlations. It's uncovering real underlying chemical truths about fermentation and quality.
It's incredible. So we have a working model. We have nearly 90% accuracy within a reasonable tolerance. We know the secret formula, or at least the most important ingredients. This brings us to our last section, implications and applications. What does this actually mean for the wine industry?
The paper outlines several huge potential applications. The first and the most immediate one that we touched on earlier is enologist support.
Right.
Imagine a lab during the harvest season. They're processing thousands of samples a day. It's chaotic. The SVM can run on the lab results instantly. It can provide a score in seconds. It can flag the problem wines or the potential superstar wines for the humans to double-check first. It helps prioritize their work.
It effectively acts as a rapid, automated triage system, a filter.
Yes. And it removes human bias. If a particular producer is very famous, a human taster might subconsciously grade them a little higher. Or if they just had a fight with their spouse, they might grade everything lower. The computer doesn't care who made the wine or what kind of day it's having. It only cares about the pH and the sulfates.
That's a huge advantage. What about for actually making the wine? Can this help the winemakers themselves before it even gets to the lab?
Absolutely. This is the production improvement angle, and it's maybe even more powerful.
Right.
Since we now know with data-backed certainty that sulfates, alcohol, and pH are the key drivers of quality, the winemaker can actively target those numbers in the vineyard and in the winery.
How would they do that?
Well, for alcohol, they can monitor the sugar levels in the grapes much more closely. If the sugar is too low to produce the target alcohol, they can wait a few more days to harvest. For volatile acidity, they can use stricter temperature controls during fermentation to inhibit the bacteria that produce it. They can essentially engineer the wine to hit the sweet spot that the algorithm has identified.
That sounds incredibly efficient, but also a little dystopian. Engineering the perfect wine with an algorithm, it takes some of the romance out of it.
It does, but the paper goes even further. They speculate about target marketing.
Yeah.
This is the future they envisioned back in 2009, and it's probably very close to reality now.
Okay, how would that work?
Well, taste is subjective, right? The Portuguese expert tasting panel might like one particular chemical profile, but what about the American market or the Chinese market? Their preferences might be different.
Sure.
So you could get a tasting panel of average American consumers to grade the same set of wines. You then train a new SVM on that data. You create an American palate algorithm.
What would that algorithm tell you?
The computer might learn that, say, Americans prefer wines with slightly higher residual sugar and lower acidity than the Portuguese experts do. Then, the winery can take that knowledge, optimize a specific batch of Vinho Verde to get a perfect 10 from the American algorithm, and then export that specific batch to New York.
Wow. Personalized wine optimized by data mining for specific demographics.
It's mass customization of what has always been an artisanal product. It helps producers in niche markets get exactly what their customers want, which reduces risk and waste.
It's fascinating. It really takes the guesswork out of the question, will this sell in that market?
And the beauty of it, the beauty of this whole paper, is that it does it using data that is already being collected. That's the key takeaway for me. They didn't invent some new expensive sensor or a fancy machine. They took the data that was already sitting in the filing cabinets, or more likely, the databases of the certification board, and they turned it into actionable, valuable insight.
This research really highlights how industries that seem very traditional, very analog, can be completely transformed by data. We tend to think of data mining as something for tech companies or finance. But here it is, right in the heart of agriculture.
And specifically in an area of agriculture that prides itself on mystery and tradition and terroir. It shows that even the most subjective of human experiences, like enjoying a beverage, have these deep underlying patterns that can be quantified and modeled if you have enough data.
It makes you wonder what else could be modeled this way. Could you model coffee preferences? Or perfume? Or cheese?
Oh, almost certainly. In fact, there are things called electronic noses and electronic tongues that are being developed for those exact purposes. But what makes this study so special and so elegant is that they didn't need exotic new sensors. They just used the standard, boring lab tests. It's a powerful lesson in resourcefulness. Use the data you already have.
Before we wrap up, I want to circle back to the methodology one last time. We talked about how the SVM won, but I'm still curious about the neural networks. Why did they seem to struggle so much, especially with the white wine dataset?
It's a great question. And it's likely due to the size and complexity of that data set. The white wine data set was much, much larger, almost 5,000 samples. And it probably had more variability, more noise, more outliers.
Okay.
And powerful neural networks, if the architecture isn't tuned absolutely perfectly, can sometimes get confused by too much noise. They can start overfitting to those outliers. The SVM's ability to ignore the small errors via that epsilon tube we talked about likely made it much more stable and robust when dealing with such a large, messy biological data set.
So sometimes being a perfectionist, like the neural network, trying to minimize every single tiny error, is actually a disadvantage.
Exactly. In a noisy, real-world system, learning what to ignore is just as important as learning what to focus on. And that's really the genius of the SVM approach that they demonstrated here.
Okay, let's wrap this up. We have journeyed from the vineyards of the Minho region in Portugal all the way to the high-dimensional feature spaces of support vector machines.
It's been quite a trip. To summarize everything for you, we saw that wine tasting, which is this bastion of human subjectivity, can actually be modeled with very high accuracy using just 11 physicochemical data points. We saw that SVMs, specifically with a Gaussian kernel, are the superior tool for this job, beating out both traditional regression and the more complex neural networks. And we learned that by using a clever technique like sensitivity analysis, we can peek inside that black box and rediscover the chemical foundations of what makes wine delicious, like the surprisingly crucial role of sulfates in indicating a healthy fermentation.
It is a true triumph of data science in a very unexpected place. But I want to leave you, our listener, with a final thought. A bit of a provocation, if you will.
Go for it.
If a computer can predict how much you will enjoy a glass of wine with nearly 90% accuracy just by measuring 11 chemicals, what does that say about the mystery of wine? What does it say about your own personal taste?
It's a humbling thought, isn't it? We like to think our palate is sophisticated, emotional, connected to memory and place.
Right. We want to believe in the romance of it all. But maybe, just maybe, you're a biological algorithm responding in a highly predictable way to a specific ratio of pH and alcohol and sulfates. The next time you take a sip of wine and you think you are tasting the terroir or the sunshine on the grapes, ask yourself, are you tasting the soul of the wine? Or are you just verifying the math?
A very sobering thought for a deep dive on alcohol.
Indeed. For those of you who want to play with the data yourselves, it is open source. The authors made it public. You can find the dataset online, fire up R or Python, and see if you can build a model that beats their SVM. Keep analyzing.
Cheers to that.
Cheers!